Hello, everybody. Welcome to the day 2 of ICLR conference. And good morning, good afternoon, and good evening, depending on where you are currently located around the globe. My name is Oluwatobi Olabi. I currently work at NVIDIA at the intersection of autonomous agents and virtual assistants. And I was formerly at Capital One, leading some of the AI research efforts on conversational AI. It is my pleasure to moderate this keynote session on AI in finance today. But there will be a couple of housekeeping items before we get started. As we watch the keynote speech, please put your question in the Zoom or Rocket chat, and I will post the questions to the speaker during the Q&A section after the presentation. It is an honor indeed to moderate this session, and the speaker is going to be Dr. Manuela Veloso. Dr. Veloso is currently the head of JP Morgan AI Research Group, which pursues fundamental research in AI in areas of core relevance to financial services, including data mining and cryptography, machine learning, explainability, and human-AI interaction. She's also a Harvard H. Simon Professor at the School of Computer Science, Carnegie Mellon University, and the past head of machine learning department. Professor Veloso is the past president of AAAI and the co-founder, trustee, and past president of Robocop. Professor Veloso has been recognized with multiple honors, including being a fellow of the ACM, IEEE, AAAS, and AAAI. She's the recipient of several Best People Awards, the Einstein Chair of Chinese Academy of Science, and ACM SIGAT Autonomous Agent Research Award, and NSF Career Award, and the Harlan Newell Medal of Excellence in Research. So please sit back and enjoy the keynote speech. And welcome once again. Thank you.
So, hi, so my name is Manuela Veloso, and I'm currently the head of JP Morgan Chase AI Research Group. And I also have been a faculty at Carnegie Mellon University as Herbert Simon University professor in the School of Computer Science at Carnegie Mellon. So I'm going to tell you a little bit about AI, in finance in particular, the scope, and give some examples. And I want to just spend one minute on AI as a science of components. AI is a science and engineering that has as goal eventually capturing every aspect of intelligence, every aspect of learning within a computer, within an algorithm, well described such that it can be simulated by an algorithm. And literally, this concept of every aspect of intelligence leads us to have many facets of such problems. So we have language, we have speech, we have computer vision, we have all sorts of cognitive functions, search, planning, learning, representation, optimization, learning from experience, negotiations, and then we do have the actual actuation. So in some sense, we know that these when we see researches in AI, this science leads into several aspects of these AI spectrum. I've been working on the integration of these perception, cognition, and action, or data decision making and action for a long time. And in particular at Carnegie Mellon, we have developed a lot of autonomous mobile robots that exhibit their perception through cameras, their cognition through algorithms, planning and learning algorithms on board. And actually these machines, these robots move, so they execute, they act in the environment. So I'm fascinated by this integration of all these capabilities into complete systems. But of course, I also understand the multiple components. And in my talk, I'll try to cover both aspects of the field of AI and as examples in the finance domain. So I just now will delve. I'll delve into this finance domain, though it was important to share that the video of the robots, that concept of autonomous robots, and I'll come back to it later, because in fact, I've been doing these autonomous robots for 30 plus years. And therefore, that's really something that I've spent a lot of time researching on. I've been at JP Morgan basically 2.5 years, almost 3. And I want now to share why it's so exciting and fascinating, this field of AI in finance. So think about JP Morgan Chase or other financial institutions that may have different types of like functions, different types of lines of business. You can think about like investment banking, retail banking, commercial banking, wealth management, asset and wealth management, and in fact also the internal cross-firm functions. So this is like the type of environment in which you now have to bring AI and machine learning to this environment. It's a very large company, and because it's so large that it produces an enormous amounts of data, and also it has the concept of having like applied AI teams close to the business and trying to get functionality across all the units. And then there is AI research that is also firm-wide, trying to bring up eventually transformation also through AI to the company. So let me just focus first on just explaining to you how we organized, in fact, these particular kind of like aspirational goals for the AI research at JP Morgan. So this is or let me just back up a second and say, so having an AI research group at JP Morgan itself is kind of like pioneering or new, because we are used to research groups at the tech companies, but within a financial industry, I think that as AI research, not apply AI, is a privilege, and it's a really wonderful place to be. So we divided these goals into like domain goals, financial domain, and we are going to focus on how to predict and in fact affect economic systems. And then we also care about this data. So we focus on how do we actually liberate this data safely, and I'll mention also something about this data goal. And then we also have this problem of eradicating financial crime. In this talk, I'm not going to focus on this aspect. And then we have 3 very interesting kind of like goals that are related to our stakeholders. Like in a firm, you have your own employees, your own customers or clients, and then you have the regulators. So most of the companies, and in particular the financial industry, has these 3 components as stakeholders. And then eventually, when we build this AI for the multiple functions, we care in our group in establishing these ethically and socially good AI also as a goal. So in some sense, you have these 7 goals that drive the research of AI research at JP Morgan. So now that we did this small introduction, I'm going to delve into analyzing with you about 3 cases, 3 projects in which these AI and finance in the AI research combines techniques of AI with important functions in the business. So let me just start with this trading problem. So we all know that traders basically follow how the markets are going, and they have to analyze these volatility of the market, these changes, and they are captured in terms of assets as time series functions on the value of these assets changing. And if you have never been to a trading floor, I had never been, we've seen it on TV, we've seen on movies, these issue about being surrounded by displays of these information in these kind of format. So when I went to this trader's floor, long ago when I joined in 2008, there was this overwhelming kind of function analysis. But the interesting thing is that I realized that after all, the decisions were guided by images. And that actually was a big aha in my mind, because the actual numbers on how the time series was changing was not being used on paper, or people were not looking at vectors of time series over time. They basically looked at images on the screen. So as we know, images have been like very successful within our machine learning community to to learn concepts through, in fact, deep neural nets. So I actually decided to see if we could actually create images of this time series data that would capture classification of buy, no buy signals. So look at, so this is very important. Was very beautiful because you can think that we are used to seeing chairs, tables being classified, and apples and oranges and cats and dogs and all sorts of like the other classification problems of objects, images of objects. But here it's images of actually time series data that we actually represented as by chopping some kind of like size of these time series. And we literally converted into some representation, candlestick. This is a candlestick representation, but then we use just with the plain function. And we basically transform it into an image, a matrix, little pixels, the actual image of this time series. And we were able to basically classify these images into buy, no buy signals, classes, two classes, by training a neural net. So look at, so what I'm excited about sharing with you is, in fact, and probably some of you have known this already, is that we could now think about using these machinery of image classification through deep neural nets to classify known objects, to classify other types of classes. So we were able to perform really well, and we have been doing these more and more and more on different types of images, and that have to do with visual input that humans take to make decisions. So I'm going just to delve a little bit more on these, reasoning through learning from images. So it's not object recognition, but it's now this reasoning through these learning from images, just along one more aspect, which is the prediction aspect. So I've shown you the classification aspect, in which we can classify these images into buy, no buy signals. And we also have done research on trying to predict, based on videos, predict interactions between multiple assets through video. And I don't think I have the time to cover that, but I'm going, or also attention focus, like specific points of like visual attention. But I'm going to focus on trying to tell you a little bit about this problem, not of classification, but of completion of an image, of the future of an image, and which will be like this prediction on time series. And the interesting thing is that we basically, again, did these neural net, is learning, this autoencoder, in which we trained this network with input up to some this gray area, and then eventually we trained with particular completions, or the rest of the time series, and we have like multiple algorithms to make the prediction. And our algorithm, this is a work done with Zheng Zhang, and then Tucker Balch and Naftali Cohen. And you'll see at the end that we have a pointer to the publications. But if you look at this visual autoencoder, visual AE, which is the Mondrian P, you'll see this pink region, and the ground truth is here in the first column. That is very well predicted. And we have all sorts in the paper, all sorts of metrics to compare how these images match the ground truth image. And it's a very thorough comparison, very kind of careful comparison. But I chose to show you also from a visual point of view, this comparison along this way. So think about the training of the neural net with being done up to 80, like in the beginning of the signal. We actually have these kind of 80 days, and then the last 20 days are the prediction part. We played with different numbers, 90, 10, other just 95, 5, all sorts of like different numbers. But the interesting thing is like this. So look at these predictions on different types of assets, different types of real signals. And the little dotted line shows up to the point that the prediction, that the input was given. And then the gray area is the ground truth of the signal, how it evolved. And the red area, the red function, the red curve is the prediction. Now, the prediction here, again, it's really very accurate. And as you can see, it kind of follows very well the real signal, the truth signal, but it's done as completing an image. And so this is why I think that it's very interesting and compelling to see these representation of the time series data as an image enables us to actually, in the comparisons we've made, to do better predictions on this completion than, in fact, using other numerical techniques. So this is a long story that I'm reducing it just to some highlights here, and I'll be, I think that it would be very exciting for to delve into this, but this is what you really, what I really wanted to tell you is this concept of really capturing time series as images. And here, just so for comparison, for example, these are other numerical machine learning methods results. The red line here shows that, in fact, the predictions are much worse, even if there is some variation, than the actual Mondrian P. So this is the first topic I told you about, and now I'm going to just rush through telling you a little bit about now other methods too that we have been using for learning, for example, in over-the-counter markets. So here is like a different scenario in which now, instead of a classification scenario, we are trying to, we are analyzing how agents actually act. So we are in a reinforcement learning scenario. But the reason why I chose these out of all the projects is because of the representation aspect too. So you think about all the markets, basically multiple agents interacting, ones like market makers that they stream prices, and investors that basically decide with which market maker they are going to transact. And so the secret here, in some sense, has been how do we actually represent these type of like problem such that we can include non-learning agents like investors eventually in this scenario, and then having these multiple market maker agents as learning agents. The secret here, or one of the aspects, is that we represent these agents in terms of like their observations, their actions, and their rewards, again, as a reinforcement learning scenario environment. But these complication of these market maker agents is captured basically by parameters. So we have a space that includes the risk aversion of these agents and the connectivity to the investor, to different investor types. So these, so we compress like what is to be learned into eventually the adjustment of this parameter space. So there is this representation in terms of like these two parameters. The risk aversion has to do, and I didn't go into the finance aspects, but it has to do with how much inventory do we hedge. So, which is like you get the positive reward from trading, and you get negative if you hold your assets for hedging. And there are some levels of like these trade-off between hedging and actually trading that is captured by how adverse these agents are to risk. So these are parameters of the domain, but by representing them over this probability distribution, you can actually then learn. So we have used a Ray reinforcement learning library for shared policy training, and we were able to show that basically these market makers can learn behaviors that are realistic and make sense. So, for example, based on the net position that a market maker has, net position is like the value of some assets. It's like the the amount that the market maker is in possession, then you can actually, in your price offering, you can actually learn to skew prices. So you adjust the relative price of bidding and asking based on your inventory, which is this net position. And interestingly, this is not something that was given, and the reinforcement learning multi-agent system was able to really learn these great behaviors. So just to finish this area, because there is a lot to think about here, because it's a problem that is not necessarily the typical game problem. It's a market, but then there is this issue about how do we represent it, and then how do we actually do the learning experiments. This simulation is very powerful, and here are two papers that you may want to look at. These Nelson Vadori and Sumitra Ganesh with Prashant Reddy and myself. We have these papers and Meng Zhu on these NeurOps this year, last year, and ICAPE, this International Conference on AI in Finance, which the first one was in 2020 and the next one is coming now for 2021. But this is a multi-agent reinforcement learning problem that is able to tune the strategies of these market makers by representing the agents with these parameters and then adjusting the parameters based on reward and simulation. One final thought here is that also the calibration of these parameters with respect to real data is very important, because eventually you want the simulation to be realistic. Also, that calibration was captured as a reinforcement learning problem in which the parameters that we change, again, are the actions of these reinforcement learning based calibrator. And that's basically the topic of the NeurOps paper. So, okay, two things I told you, like Mondrian classification, Mondrian prediction, based all on image classification. And here now the reinforcement learning aspect. And I'll tell you one more thing while I still have a few minutes, which is based on something that's very important for me, which has been like this interaction with a specific AI algorithm, an intelligent AI system, in particular at CMU with the cobot robot. We basically set requests for this robot. Go to Manuela's office, bring this coffee to some place, go to the lab, do this. It was all language that was basically translated into execution and learning. So the robot is able to ask, I don't know what you mean by coffee, and eventually it learns by interacting with the humans, not necessarily by being given a lot of classified data, but by this interaction. And now, based on this, I'm going to show you something that is very important at JP Morgan, which is basically document generation. So we have to create reports, PowerPoint slides, all sorts of like translation of a representation, which is all these tables, maybe Excel tables, speech conversations with clients, journeys of people using like the multiple products of the firm. So there is all this activity, all this history, like the robot moving around. There is all this history, and then eventually there is a need to understand what's going on there. And most of the time, this is done by transforming that representation into something else, pie charts, histograms, heat maps, all sorts of like language capturing insights. I mean, it's a very interesting problem of representation change. So we automated this along some dimensions, and we created this DocuBot, which is a bot for a document generator bot. And in particular, AIPPTX generates basically based on image, on language, some slides. So I'm just going to go over these final video just to show you an example of this DocuBot. And I'm going to just fast forward this and just show you this is work with Vineet and Rafi, Salima Muri, and Armine Norbarch, and Andrea Stefanucci, and Samina Shah and myself. So here it is. So think about this problem of actually asking some kind of like AI system, a DocuBot, how can I help you today? Please template for the last POV by order for company ticker XYZ today. So basically you have language and you now learn to map this language to really like parameters of this template. So all these slides are generated automatically from the language to this new representation, which is pre-specified one way or another, like through this template, but then all the parameters are in fact learned to do the right mapping. And in fact, I'm going to show you here an example in which DocuBot actually, when asked to make changes, it can ask when it does not know. For example, center the figure title. DocuBot might not have learned what center the figure title means, and then it asks, shall I make the change for all the figures or for a specific figure? And then the user may say, for all the figures, I believe here it's what it says, and it learns this mapping between center the figure title. Next time you interact with DocuBot, it might suggest, do you mean all the figures? So this amazing interaction between DocuBot and the user is a learning experience from beginning to end. And DocuBot accepts commands of the sort that changes the appearance of the slides, colors and centered and size. It accepts commands that change the content of the slides, change the data, give me 4 years instead of 8, and also it can actually save these commands that I gave you into a new template. So you are learning new templates, you are learning to adapt an existing template, and you are able to actually revise. So this is a very kind of beautiful example of, in fact, these learning by interaction with humans of performing, like the robot moving around, a complete cycle of getting the data, thinking about what to do and learning and actually doing. So the slides are all generated automatically. So here is an example in which there was the user asked for an additional heat map and here at the end of the presentation. So in summary, there are many other projects that I work on, that we work on as AI research. I mean, we have these document and information discovery, lots of learning, customer satisfaction, detection and prevention of financial crime, regulation and compliance, all sorts of like fairness in markets, ethics and values, and a lot of research on trying to improve the client experience. So, it's a large group, and all that we do falls within these 7 categories. I invite you to go to this publication place in which we have actually the description of our work on jpmorgan.com/AI, as well as publications that I also have available off my CMU webpage. So as we still have a few minutes, I'm just going to give you one final thought in terms of learning and representation of great impact in AI in finance. So, okay, by the way, if you want to send me email, it's just manuela.veloso@jpmorganchase.com. But I want to just spend 1 minute on this additional project. I was just saving it in case we had like a few minutes left, which I think we do, which is this very interesting problem that of like, how can I say, automatically transforming data in multiple representations to a standardized representation. So what happens is the following. So financial data is stored in a huge variety of Excel files, tabular formats. And it's literally in a non-standard form. So it's kind of like difficult for a machine learning system to use financial data coming from multiple sources because the format of the data, the representation, is so non-uniform. So Armin and Norbarch in our group and Samina Shah literally, especially also Arminet, got tired of really like these constant fixing up the data so that the machine learning could extract the patterns, could transform the representation to input to DocuBot, and so forth. So we have introduced these standardized financial extraction AI, these Sphinx, that converts the data in any format, Excel, into a unified standard form. So it's able to basically, it's a wonderful AI kind of system that is able to understand these multiple titles of columns, USD in million, and is able to convert this particular kind of representation to a standard financial data representation. Here we mean by financial data, basically tables of numbers changing over time. So I'll show you this, which is really interesting. So here is the example that was just in the previous slide. But if you spend some time looking at this, it is converted like this number 2187, it's here as a value. So the financial data is always converted into metrics, submetrics, sub-submetrics, as period start, period end, value type, and scale. And this scale, for example, in US dollars is extracted from these titles. So this is natural language basically parsing that or mining that representation to extract all this information that then you can use in the standardized representation. And just for a feeling of how compelling this is from my point of view, look at this beautiful kind of different financial data. The macroeconomic is there, rates and inflations now are, instead of being represented like these, are per row. And also this is transformed to the same representation. So I just wanted to finish, and I can come back to this just to tell you that indeed, just to finish, that this is the AI in finance is a fascinating field of like trying to bring AI to really through large scale and challenging representations, be it numbers, be it time series like represented visually, the whole operation, the whole thinking is all about data, is all about information. And I did not focus here, except for the Sphinx example, on all the work we do on looking at actually textual data, documents, hundreds of documents that then you can extract a lot of information from. So I believe we are out of time. I forget when we started, but I think we're out of time. And please send me email if you want to know more about AI in finance. Visit our website. I believe our revised external website is going to be available soon. And I thank you very much for this invitation. And I hope to hear from you.
Hi, hello everybody. This is Oluwatobi Olabi once again. We have now completed the presentation part of the keynote speech. We are moving into the question and answer section. Please post all your questions. That was something I got wrong initially. Post your question on the Rocket chat on the website, and the moderators are going to bring it into the Zoom chat for us to have the discussion and have Professor Veloso taking the questions and answering them. So welcome, Manuela, to the Q&A session. We already have a couple of questions coming in, and I'll be posting them on behalf of the people asking the questions. So the question one here, it says, do you have any uncertainty band on the prediction of the time series prediction?
Yes, so this is a very good question. Definitely, we have a range, and we have uncertainty as the machine learning model outputs the prediction. We use the certainty that the machine learning model has on the multiple levels of prediction. And as you saw, probably, or maybe I don't know if I explained. I don't remember if I explained it in detail. This was pre-recorded. But for every time step in the future, we have different predictions. And therefore, the predictions that are closer to the moment you have a higher confidence than 20 minutes later, or 20 time steps later. And so that's basically, yes, we have these predictions.
Okay, thank you so much. So the second question is about how you created the training data for the time series images. And the question is, how did you create the patches, the image patches? Did you do cropping? And how did you handle different scales of time period?
Okay, so this is a parameter of the system, but I want you to understand that this time series data, and also answering the next question, how do you know why image representation work back then, numerical methods? So what happens is that these time series data is actually represented as an image, So think about the picture of an apple and an orange, or a cat and a dog. They are images. And images have been used to basically capture a lot of objects. Here you are basically creating a plot of a time series data into an actual image, all white, except for some kind of like non-white pixels that represent the time series going. Okay, so the length of the width of that image, how many steps we use of the time series to train, is one variable of the system, one parameter of the system. We tried several. I believe we currently were using 20 minutes of time series data of the financial data. We did in other time series, but on the financial data, I think we used 20 minutes, and we basically chop the image, create that image and train with that. Why is this better than numerical methods? Well, I believe that numerical methods suffer more from the actual numbers themselves, and the variations of the numbers, whether it's like, imagine an interval from 100 to 120, or an interval from $1 to like $1.05. And so they probably are more sensitive to that type of like variation of the actual values. And the image just gets like the shape of the dynamics of the time series. And the beautiful thing about this work, again, is to show that basically that visual information can be used in addition or instead of the numerical information.
Okay, thank you so much for the response to the question. I think now we're moving into the multi-agent market maker section of the talk. And the question is, when defining the binary problem, buy, no buy, do you also consider the symmetric problem, sell, no sell? And if so, do you weigh both models to ultimately make a decision for whether to buy or no action or sell?
We have not done that, but yes, we were. So basically, we have not done yet. We were like just using these buy, no buy signals, which were actually, so the no buy was when you didn't buy. So we basically used all the data available, and you just think about a window moving over time, and we chopped these 20 minutes. We got the time series data for those 20 minutes, and then basically we associated whether the traders bought or not bought the actual asset. And that's how you train the system. We were using we didn't use sell data, but again, we could. It's the point here that matters is that we are able to associate a decision, not a classification of an object, with the actual image. And so when we have done these in several other scenarios, other images of other nature.
Excellent. Thank you so much. So going again on the representation aspects, the question here says, in some domain, like pathology in medical imaging, the representation and color code has shown to affect the performance. Did you try different representation of the images of the graph? Like, did you try different color for the plots?
A very good question. In fact, you are right. You just touched this very important domain, which is medical imaging. And again, you know that doctors are masters of using images or using their what they see to extract a lot of information from the image representation, be it like we are pale or we have like deep circles around our eyes. Everything is used in terms of like the image, let alone like the EEG numbers. Everything is kind of used to make a diagnosis, to make a prediction, to make a classification. So indeed, we tried different representation. We tried, as you probably saw on the talk, we use this candlestick-like representation, which is associating amplitudes with little black or white bars, if it's like going up or down. And we tried just the actual dots in the image for the time series. We did not use color so far, it's true, but I think that actually the very first initial version, the background was not white, was blue, and the signal was, I don't know, dark, black or red. So I think that everything is like an open kind of like area of research on what the image should look like. But we did try several and it didn't affect that much the results. So we went to just this black and white picture that captures the signal.
Okay, yeah, thank you. So the next question is touching the last section, which is talking about human and machine interaction, learning from those interactions. And the question says that, can you elaborate on the input and label of training data of DocuBot, as well as the learning objectives to train it?
Okay, this is a very good question. So let's be clear here. DocuBot only learns through interaction with the humans. It doesn't learn from any training data. So there is no accumulation of data. DocuBot basically, or let's see, DocuBot basically is able to map a language that people ask, please plot these, please do that, turn these into that, and map these into actions that it can take with respect to that translation of the data. So those mappings from language to actions were indeed trained on some data with a limited vocabulary, but the science there is not that initial training phase, but it's the interaction in the next interaction. So what happens is that then when a human says, okay, center the figure or do some kind of language, and the DocuBot does not have anything mapped to that type of like language, it asks the human, what do you mean? And as the human responds to this type of like, what do you mean? Then the knowledge that the DocuBot has gets updated. So it's kind of like a continuous learning system rather than a training system. So if you have not, so you could have started it tabula rasa with no training at all, but then the interaction would have been tedious from day one, like make these particular kind of like a customer report, and immediately DocuBot would ask, I don't know, what is this report? Tell me what is this report? And then the person had to explain, go to that particular file and blah, and the DocuBot would map that request in language to that kind of action it can take. So the science there is the same way that we did in with our robots at CMU. The concept is that it will never stop learning. So it has learned something, it maps some language to some actions, but as soon as the human uses some language that it's not clear and not mapped to anything inside of like the knowledge base of the robot, it just asks, I mean, in this case, DocuBot, it just asks. The human answers, and their answer is encapsulated back into the knowledge base. So so here is like why I like so much to talk about this paradigm in which this is learning from experience. This is continuous learning. It's not like you collect all this data, these are all the cats of the world, you give them to some neural net, and magically the neural net knows now what's a cat for eternity. This is not really what's going on here. It's that you start the system with some kind of like mapping from some language to some skills, and then as it goes, it's just capable of asking for help. This DocuBot is like saying, I don't know what you mean, tell me. The person says, DocuBot learns. And it's continuously on these, tell me what you mean, answer, and absorbs that answer. If the person said something wrong, okay, big deal. Next time the robot is going to, or the DocuBot is going to propose, is this what you mean? The person says, no, I meant this. And over time, it converges to have the right mapping. Wow, this is a long question here. Playful.
Yeah.
Okay.
Yeah. So before we get to that, there's question 7, which says, was buy or no buy decision also tried on prices of cryptocurrencies?
Not really.
Just stock markets. Okay.
Not really, but on the other hand, I tell you, the principle of using images as time series, it doesn't really matter as much what is the actual target. And to tell you frankly, I cannot even say not really. We have applied it to so many scenarios that maybe we have done cryptocurrencies yet, but I don't think so. Okay, but think about this. The only thing we are capturing is how some variable, the price of some asset or the price of some cryptocurrency, varies over time. So you get all these little kind of like time series data up and down and all of that, and you basically use this as an image. Don't forget that we really are not putting any semantics on how it's changing. It's just the actual image. And then humans magically see, oh, this is going deep, 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 deep. Well, if it's going up, so it's going to also probably go slow up. Who knows what we see? But the machine is able to learn these dynamics,
Okay, thank you. Thank you so much. The next question says, has any of your code for reasoning from images or numerical data extraction from spreadsheets been open sourced? Please advise. If yes, can you please share the link? And B, while charting is popular among traders, as per my understanding, it's scarcely considered a science. And charting is thought to be like a self-fulfilling prophecy that depends on the sufficient number of traders believing in it. Can widespread adoption of representing numeric data as images possibly increase systemic risk?
It's a deep question. So first of all, the code now to do the classification of images as time series data will be available soon. It's not yet in a shape that's like so polished that can be made open, that people can use with all these parameters and all these things. But keep in touch, Manuela.veloso@jpmorgan.com. Send me email. We'll keep you in this list. There are several people that are in the mailing list waiting for this code to be made open source. So charting, this is very interesting. Don't forget that indeed these kind of like appearance of the data is not us who have invented it. If you go to a trader's floor, if you go to conversations among traders, then basically they are always looking at how things are changing over time. This particular kind of like display of time series data is very common for humans to reason about what to do. So I'm not sure what you mean by not consider the science, but in some sense, it's not a science or less science. It's just a fact that people have used images of time series data to make decisions. And the last one, which you say, can widespread adoption of representing as images possibly increase systematic risk. What I want you to understand is that this is we are in this conference of representation, the value of representation. This is a representation kind of contribution, okay? So whether it's used better or worse, I don't know. But the point is like this: when have we talked often about using an image as the representation of a time series? It's not really common. We have been talking about representing language and embeddings. We talk about representing, all sorts of objects as image. We talk about like so many representations. Okay, so the interesting thing here is like, okay, guess what? Time series data can be represented also as an image. That's the main thing. Now, whether we, for example, we have been doing video also, multiple images and animating multiple time series correlations. We have been trying to move on. And the only thing I'm saying to this audience, and you guys are the experts in representations, I love representations from an AI point of view. It's really fascinating, this concept of representing concepts in different ways. I'm telling you, we even are looking at correlations between time series data that goes up and down as videos that show the stretch, show how things are correlated, instead of necessarily depending so much on the actual numbers. So we are just going one step ahead and bringing in 2021 to everybody's consideration that in addition to speech and text, there are what we see, and what we see besides objects has a lot to do with other displays of information, that it's not only objects. And in some sense, you know that being it doctors, being it scientists, being it us teachers, when we teach something, how much we know that wonderful quote, like a picture is worth 1,000 words, right? So there you go. Let's delve into pictures that capture other things than actual objects. That's basically what I'm trying to say. Okay.
Awesome. Thank you. So the next question probably is continuing on that thought, that have you seen any non-traditional statistical techniques outperforming older or traditional statistical-based techniques, but for this particular purpose, for credit risk prediction, like for default prediction, for example, based on external or internal ratings when they exist? Please advise. If yes, can you elaborate on the same?
Very good question. Again, my talk or my thoughts are not exactly on advice at the financial
decision-making
level. See, so I did not didn't organize the task to be a financial domain
specific.
See what I'm saying? So
yeah.
I cannot say much about kinds of errors in all these. So that's not the focus, and I'll be happy to do another talk just on finances. This was a talk on the value of representation, while in fact within the financial domain, but it was just to alert everybody, whether they're in finance or not, of these new things that we are working on. And I do insist, I mean, I see that, it's always Mondrian that tracks more questions, and okay, 1 or 2 in DocuBot, perfect. But you know what, that multi-agent kind of like calibration and the multi-agent prediction is absolutely fantastic from the point of view of looking at something. So, you look at this very complex domain as a financial domain, as a multi-agent simulation, and you are able to have these agents learn strategy that is very kind of like real, very realistic. So this is also another type of like a representation contribution, because some sense by capturing these agents with types that had like parameters, now you embed all the complexity of what an agent is into these vector of parameters. And somehow the learning goes into this vector of parameters until eventually it adjusts them into something that is learnable and makes sense learning. So think about all of these things I told you, and I was listening to my talk and I didn't emphasize it enough. These are all representation contributions, the images, the agents as like vectors of type. So all this confusion, what do they want, their intention, their this, their that, okay. Let's capture a space of features, a space of types, a space of parameters, and then let's adjust them to achieve some value. And then the DocuBot comes as the representation, this change of representation. What's DocuBot is so beautiful is the fact that internally it's all these numbers, all these kind of tables, and then magically you have to translate these into some charts, and you have to translate these into some language. And now you automate, in some sense, and learn this change of representation with the input from a human. But you are trying to say, yeah, that's it. This representation can be changed automatically through AI to another representation. So it's not French to English or Chinese to Portuguese or French or Italian to English, whatever. It's like, okay, from these tables and databases to something else. That includes language and charts that humans understand better. So it's all about this wonderful area of bringing AI and learning to the space of playing with representation.
Awesome. Thank you for digging deep into that. Our time is almost up, but we'll take a couple of more questions. So this is very interesting. So do you have a sense of the kind of error made by a visual buy or sell predictor versus a time series-based buy or sell predictor? Do they seem to have different biases and make categorically different errors? So that's
a very good point. We did compare the image-based trained neural net with an actual numerical-based neural net. The difference is not major, okay? However, when you represent data of time series data to be used with actual numbers, with actual values, you have to be very careful, because in order to learn from something that varies between 100 and 200 and 1 and 2, you have to normalize. Otherwise, a neural net is going to get attached to those numbers, 100, 105, and then you give numbers 1 and 1.5, and it does not really learn, while the image base learns basically shape, and the other one is very sensitive to the actual numbers, the representation of the numbers. So, but again, I don't have an actual, how do you say, scientific answer to these, or good experiments that tell me about the kinds of errors, and I don't know. This is all questions that anyone can now pursue. But again, the important thing is to understand that magically, in quotes, magically, a time series data that is being treated as a bunch of numbers, as a vector of numbers, an LSTM or whatever you want to do, you don't need to do any of that. You capture that as an image, and there you are. So that's, again, look at the beautiful thing. We have invented these machine learning techniques to capture temporal sequence, LSTMs, and so forth. And now, okay, what about if we can represent that temporal sequence in an image that captures the dynamics? Okay, maybe we can just use that image. And I tell you another example. I mean, if you want to go to my website for publications at Carnegie Mellon, something interesting, I mean, it also has the ones at JP Morgan more recently, something interesting we did in the old days with robot soccer, it doesn't matter. So these robots move on the field like crazy, and we wanted to learn what the adversarial team was doing. And we basically used the whole trajectory, not actually what they were doing at every moment. We compiled an episode, and that became a curve, which was a trajectory. And we used those lines. I mean, we didn't use as image. We had other methods of comparing them. But I think there is some science here and some interesting insights about representing things that are changing over time as like their dynamics in one shot. Anyway.
Yeah, okay, thank you. Yeah, thank you so much. I think our time is fast going, but I actually have a couple of questions even from my own side to you. So okay. One question is, given all the kind of experiments we've done in this different problem space, so what do you think about using an end-to-end approach and pipeline approach in building autonomous agents, in which you have different modules that are connected together in series, or to just go from actual feature space and go to make prediction? Which one do you find more useful or rewarding in the work you've done?
Okay, so this is a good question too. So I do think that I have spent all my life doing end-to-end solutions, because when I build autonomous robots, I mean, that was end-to-end. You have to process the vision, feed it up to some planner, and then eventually feed it to some motors that the robot moves and continuously get more info. So I'm very, how do you say, experience and passion about end-to-end solutions. However, I have to tell you that when we build end-to-end solutions, the secret is that we have to break everything into pieces, the little skills, okay, go to point, or DocuBot, which is plot a little kind of like pie chart. So if we don't break into pieces, even when we put everything together, first, we cannot improve the pieces, and we cannot reuse them, second. So what I'm saying is like this, end-to-end problems are hard to build. And then the next end-to-end, if it cannot transfer anything from the previous one, it's a nightmare. So, for example, when we did robot soccer, the big thing was to do then mini golf also with the same robots, without having, again, end-to-end, but without having to redo everything. So in DocuBot also, don't forget, and I don't emphasize here enough, DocuBot is used for many different types of documents. The PowerPoint documents, charts, it generates text. The 10Q is a report very common in companies that are quarterly reports about how the company is doing. It's all language, no charts. It's also done by DocuBot. It's all different types of translations. But the fact is that while building the end-to-end system, you build these components and then they are all reused. So,
okay.
So this is like, I tell you, this is the secret. I mean, I love end-to-end, but if you do end-to-end every time starting from scratch, you just do a few in your lifetime.
Yeah, I think we are right on time. Thank you so much for your
Thank
time.
you so much.
Really appreciate all the questions, and people who ask those questions. Thank you for answering them, for asking them, and for those other remaining questions we couldn't take, you can reach out directly, or Manuel can probably reply to you directly on the Rocket chat, or you can reach out to her directly through our email, which she had already given during the talk. Thank you for your time.
Thank you very much.